Lesson 35, transformations of sine and cosine functions. All right, so now we're just going to get more into the nitty-gritty of doing our transformations like what we've been doing in the other lessons. So a lot of this will be familiar, but it just kind of has a bit of a unique twist with sine functions. So here is our equation. So we've got A, B, it's now C and D, right? Before it was H and K, but it's the same idea. This is still going to be our horizontal translation, and this will be our vertical translation, right? Okay, now A, like we were saying in the last lesson there, this will always be the amplitude of your graph. So to remind you of what that means, right? The amplitude was how, high up it comes, right? So this is your amplitude right there, or there, doesn't matter, it's absolute value, right? So that's your amplitude. Your B value is going to be your horizontal stretch. So that's, if this thing was like an accordion, right? Is it being stretched inward or is it being stretched outward, right? And it's going to be backwards again, right? So it's 1 over B is the horizontal stretch. So same thing. It's always the opposite of the way it goes in the actual function, right? The 1 over B, why this is going to be important is your B value is going to strongly relate to the period of the function. Okay, so that's that P is equal to 2 pi over B or 360 over B. Okay, and I'll show you some examples of that. Now, if you remember from the last lesson there too, the period is equal to pi over B instead of 2 pi over B for tangent functions. And do you remember that? Because the tangent functions, the period was actually only pi instead of it being 2 pi, right? It just happens, at closer intervals, right? Okay, so now the new stuff I didn't talk about in the last lesson, our C value is going to be your horizontal translation, or phase shift is what it's typically called when we're talking about sinusoidal functions. And your D value is your vertical translation, so that is going to be moving the whole graph up or down, right? It's going to be actually just moving that midline up or down, the whole graph, but yeah, that's what we can kind of think about as being the thing moving. So, okay, and then some things to note. If your A value is less than 0, then the graph is going to be a reflection over the x-axis. That should be familiar because that's the same way it's always been, right? If your A value, if your number up front was negative, then that just meant that we had a reflection in the x-axis. Okay, that's going to be the same thing now. If your B value is negative, then that's going to be a reflection in the y-axis. If your C value is positive, the graph is going to translate to the left, right? So that's the opposite of what you think still. If it's negative, it's going to go to the right. And then your D value is what you think it would be. So if your D value goes down, it goes down. If it's up, it goes up. So like I said, like what we've been doing. So let's jump into this. This one says, graph one complete cycle for each trigonometric function on the grid provided. All right, so what I'm going to do here to begin with, though, is I'm going to graph out just the base function. Y is equal to sine theta, right? That's a good starting place. And then we can kind of see what effects this is having on our graph. So if we remember sine theta, right? That's saying what's our y values at any given point. So right here at this point on our unit circle, right? So this is our unit circle going around. Better than that, but that'd be the point 1, 0, like right where you started. So our y value, right, is 0. So our sine graphs do start at 0, right? Cosine graphs start at 1. Sine graphs start at the origin or start at 0. All right, and then the next kind of relevant point that's going to be useful for plotting would be when it's straight up and down, right? So when it's straight up and down, right, that point right there, that would be the point 0, 1. And where did that happen? That happened at 90 degrees. So we're going to be up at 1. There, you know what? To fit this, I better make my 1 different. Well, actually, no, that'll be fine for this one. Sorry. So my 1, I'll make it here. All right, so now when I'm figuring out what my scale needs to be on the x-axis here, or my angle, let's think about what typically just sine theta, 1 full cycle would be 2 pi, right? So I need to go all the way up to 6 pi. And how do I know I need to go up to 6 pi? Well, look at our B value. It's 1 over 3, right? So that means I'm going to have a horizontal stretch. So a horizontal stretch of 3, right? So that means all of my x values are going to be multiplied by 3 here. So Yes, let's make sure we go up to 2 pi, or at least have 2 pi on the scale here. Or 6 pi, I mean, sorry. All right, so to do that, I went every, you can see the mark that just probably showed up for you, every 6 blocks. So I'll make that 2 pi, and that'll be 4 pi, and that'll be 6 pi, right? And then I'll kind of fill in the middle here. So this would be just pi, and this would be 3 pi, and 5 pi. All right, so that should be good enough. We can kind of fill in the rest as we go here. Oh, and we'll make this -1 as well. All right, so let's just graph our standard sine function, right? It's gonna look a little distorted on this graph because I have big spaces for my y and it'll be little spaces for my x, but it'll be all right. So one full function for 2 pi here. Okay, so that would be, well, it would start here at pi over 2, so right in the middle, it's going to be at its peak. And then it's going to come back down at pi. And then at 3 pi over 4, or sorry, 3 pi over 2, I should say. It'll be there. And then back up there, right? So that would be my one cycle for just the function sine theta, right? Now, we'll think about it this way. Let's actually like put the points for like the values for some of these points. So this would be the point 0, 0. This one would be the point pi over 2. Come on, pi over 2, comma 1. And this point would be pi, comma 0. This point here would be 3 pi over 2, comma -1. And then this point here would be at 2 pi, comma 0. All right. So now the reason why I wrote those out, I won't do this every time, but I just want you to remember these are our x values, right? So x value, yeah, all the way around. When we're making this horizontal stretch of 3, well, what that's doing is that's stretching every one of these x values, right? So every one of these x values is being multiplied by 3. So let's see where the pi over 2 ends up, right? So I'm going to multiply pi over 2 times 3. So this value here, right, of pi over 2, comma 1, right? That's my x value, that's my y value. Where will this become? Well, this is going to be now turn into the point pi over 2 times my stretch factor of 3. So this is 3 pi over 2, right? So this point, we'll make this a different color now so it doesn't get so confusing, is going to be at the point 3 pi over 2. So that's over here. Okay, that makes sense, doesn't it? This is 3 times farther away than this one, right? This was that far away, and now this is 3 times farther away. It's been stretched by 3 times that in that direction. Okay. Maybe I should have done this one first, but where would the point 0, 0 go? If I go 0 times 3, well, that's actually at the same point, isn't it? All right, so far, if we're just kind of piecing this together, we are here, and that's my max now, right? So then let's look at this point here. This was pi. Well, I'm going to multiply that by 3, so I should now be at 3 pi, right? So it would go up, it would come back down again. And then you know what? We could do that for every one of the other points, but this thing, you see the pattern once you get going, don't you? That I am going to end at 6 pi, right? And then I'm going to come down here, down to 1. That was too far. Down to 1. I'm going to be in between those, and then back up again. And that should be like right there, right? So we can piece that together. We can tell what that point should have been, right? That was this point. That point moved over here. So that was really 3 pi over 2. And then if we multiplied that by 3, that would be equal to the point 9 pi over 2. Right? That's what that point would be right there. So there we go. We sketched that graph. So now remember that these could also be written in degrees as well, right? I did it in radians, but this could have been done the same way in degrees. We just would have been multiplying our degrees by 3 every time instead. All right, let's do the next one here. So now we have y is equal to -2 cos and then 4 theta. All right, so if I'm looking at this one, what we're going to do here is, well, you know what? I could piece it together like the last one too, right? Because I can look at this and say, okay, what do we got going on there? We have a vertical stretch of -2, so that'll be flipping it. So we could sketch out the cos function and then do, you know, a stretch of this and then horizontal stretch of 1/4. But you know what? I find once you start getting like, you know, anything above 1 or 2 different transformations, it's a lot easier to use our mapping notation. Okay, so let's make a mapping rule for this thing right off the bat. Okay, so let's make a mapping rule. So this would be, well, here, actually, right off the bat, let's write down what we have going on. We have a vertical stretch of 2, right? And then, yeah, because that's our A value. If you like, we can also just say it's a vertical stretch of -2, couldn't we? Because that actually just handles the flipping of it over the x-axis, right? If you want to, you could say vertical stretch of 2 and a reflection over the x-axis, but whatever, vertical stretch of -2. That means the same thing, right? Multiplying by -2. And then we have a horizontal stretch of, and then it's 1/4, right? So 1/4. So let's make a mapping rule for this. So this would mean any given point on this graph, right, would turn into, so xy. So my x's would all be multiplied by 1/4, and my y's would all be multiplied by -2. Oh, sorry, I should finish that. 1/4 x, and then my y's would be multiplied by -2y for that y value, okay? So there's our mapping rule. That's our key, right? So now what we can do is say any point on the original function, just y is equal to cos theta, right? Just our standard graph. Let's just take some of those key points like what we did in the last one, right? Those, you know, pi/2 and, you know, all those nice points on the unit circle. And we'll just figure out where they went. And we'll just find those new points on the new graph, okay? Just using this mapping notation. Okay, now, so if I'm trying to figure out my scale here, then let's look at the scale for our y's, and I'm really focused in on this number. So -2, that means I'm going to have a stretch -2 up and down at some point. It's going to be reflected because of the negative, but either way I'm going up 2 and I'm going down 2. So I got to be able to go 2 up and 2 down. So I think it'll still work to call this 1, but I know I'm going to be all the way up here at 2 as well, and then do the same on the bottom. So then we're -1 and -2. Okay. For our scale on the x here, well, I have a horizontal stretch of 1/4, right? So if I want to see the, like, just one full stretch of this thing, then I can really see, well, pi/2 would be normally the period I'd need to be able to see. I need to see like just 1/4 of that. So as far as I need to see would be pi/2 divided by 1/4, right? So that'd be the same thing as just multiplying by, so that'd be the same thing as pi, or 2 pi. What am I doing? It's not pi/2. 2 pi. I'd normally want to see 2 pi. Sorry guys. So 2 pi, and I'm going to divide that by 1/4. That makes more sense. Okay, so all right, so now figuring out how far I want to go on the x-axis here. Well, typically, if I just had cosine theta, I would want to see all the way to 2 pi, right? That'd be one full cycle. But my horizontal stretch is just going to be 1/4 of that. Okay, so in that case, then what we could do is say, we could just take our 2 pi. Come on, pen, you can do it. There we go, got it back. All right, so 2 pi, our normal scale there, right? And let's just divide that by 4, or multiply by 1/4, either way. So I only need to see one full cycle would only be pi/2 is as far as I need to go, right? All right, so first thing we're going to do here, I'm going to graph just so we can like see what's going on here too. Let's graph y is equal to cosine theta, just so we can, see what we're doing. So cosine theta would go all the way to 2 pi if we want to see all of our points there. So in that case, let's make every 4 blocks would be pi over 2. So that'd be our pi over 2. And then another 4, we'll call that just pi. And then another 4 would be 3 pi over 2. And then 2 pi. All right. And then our standard cosine graph starts at 1. And then it would come down through pi, or pi over 2. And then back over to pi would be there. And then there. And then at 2 pi, we're back to 1. All right, so that's our graph. So let's connect the dots here. All right, so we want to see what happens to that, right? So let's start off with the point right here, right where we started, the point 0, 1. Where does this go? All right, so this point will now be at, well, our x value is 0, so that's going to be still 0, right? 0 times 1 over 4 is 0. And then our y value is going to be -2, and then 1, right? So our y value would be at 0, -2. All right, so where is that? Let's do it in red. So that's down here, right? So now that point is down here. Okay? And then we'll move on to the next one. So our next point, let's do pi over 2, 0. So the point pi over 2, 0 will become the point, and then that would be 1 over 4 times pi over 2, would be this part of it, right? Comma, and then -2 times, and then our y value there is 0. Okay, so that point will become pi over 8, 0. All right, so where is that? Okay, well, that point, so when we're at 0 here, is going to be, so anyway, our y value is 0, so I know I'm on the x-axis. Now, if you think about it here, if you go half of pi over 2, right, so like into here, where would that be? That would be pi over 4, wouldn't it? Right, that'd be half of pi over 2. So if I want pi over 8, right, so this pi over 4, pi over 8 would be in between those, right? So pi over 8 would be right there. Okay, so that's where I'm at in that one. All right, so let's keep going here. So now we'll have, so let's do this point now. So this point here was the point pi, -1. Okay, so let's do that one. So that would be pi -1 would become 1 over 4 times pi. And then comma, and then this is -2 times -1. So where does this become? This would be the point pi over 4, which we know where that is, comma, and then -2 times -1 is 2. That makes sense. That's going to be our new max, isn't it? It was the min before, and now that'll be the new max. So where is that? So pi over 4, 2. So pi over 4 we already found it the first time, right? So that's going to be way up here. And then I think we're getting the idea, aren't we? Let's do one more to kind of make sure we're on the right track here. So now let's do this 3 pi over 2. So this point was 3 pi over 2, 0. All right, so 3 pi over 2. Come on, pen. 3 pi over 2 0. All right, so where does this point become? So that's going to be again 1 over 4. Our x value is 3 pi over 2. comma, and then this would be negative 2 times 0. All right, so that would become 3 pi over 8, comma, and then 0. All right, so now where is 3 pi over 8? Right? Well, 3 pi over 8, let's think about it this way. Remember, this one was 1 pi over 8, right? That was pi over 8. And we just have 3 of them, so it's going to be 1, 2. That gets me here, which is what I expected, isn't it? Just based on like the general shape of the graph there. Okay, and then you're probably guessing that the next one is going to be down here, and you'd be correct, right? That would be enough. We could do it. I'm getting tired of doing it, so we'll just start there. So this graph would come up. I'm probably not going to do this justice because it's so squashed now, but this would come up. Oh shoot, I'm already wrong. Go all the way up there, and then come down, and then something like that. Okay, so there you go. There's our new transformed function. So it started out looking like the green line, ended up looking like the red line. All right, let's move on. Okay, so we're going to sketch the graph of the function y is equal to 5 sine, all that, right? Showing at least 2 complete cycles. Describe the transformations and then state the domain and range. Okay, so just like in the previous units there, I think a good place to start is going to be to figure out all my different transformations here. So let's start from the beginning. So we've got this 5. What is this telling us? We have I'm going to write them on the left here just so we have more room on the right when we start doing it. So we have a vertical stretch of 5. We have well, what would this do? Okay, maybe let's write that instead as 1 over 2, right? So you can see now that I have a horizontal stretch of 2. Right, just the inverse of those. Okay, we have a horizontal translation of, and then remember this is backwards, right? So when we have our C value, like our phase shift, or horizontal stretch, horizontal translation, it's going to be the opposite. So this would be of pi over 2 to the left, or negative pi over 2, sure. And then lastly, we just have our vertical translation of 3 up, or positive 3 if you like. Okay, so those are the things we're going to do, right? So that just kind of helps to get those written down. So now we got to figure out what we're going to do for our axis, right? Or our axes. So if we can imagine here, you might say, okay, we got to make sure, since we have a vertical stretch, that we got to go up at least a 5, right? But the problem is that the whole thing has a vertical translation of 3. So this whole graph is being moved upward, right? So we actually have to go all the way up to, you'd move the whole thing up 3, and then from there we go 5 up. So I need to go at least to 8. I got to be at least to 8 on the top side of this thing. All right, so now that we have that one figured out, oh, here, sorry, let's fill that in. So this would go up by 2. Right, so this would be like 2, 4, 6, and then we should see the top if we go to 8 that way. And then the bottom will be negative 2, negative 4, negative 6, and negative 8. All right, so we got that one figured out. Now, how far to the right are we going to go, right? Well, to figure that one out, we need to figure out what the period of this graph is going to be. So let's figure out our period right now, just so we know how far we need to go. So period is equal to 2 pi over b, right? It was also b is equal to 2 pi over period, but I want to figure out what my period is right now. So we'll go period is equal to 2 pi over b, so that's period's equal to 2 pi over, and then our b value was 1 over 2, so that's going to be equal to 4 pi. Okay. So that's useful. That's the period for this graph. So I know I need to go at least to 4 pi, but actually it says showing at least 2 cycles, right? So it wants like 2 times that. So we need to go up to 8 pi. Okay, so we'll just make our scale so we go all the way up to 8 pi. So I think this will work out if we just make every 2 boxes will be pi, right? So that'd be pi. So 1, 2, 3, 7, and then 8. All right, so just make it so it's not maybe so crowded. I'll just only label 2 pi and then 4 pi. And then 6 pi and then 8 pi. All right, so our labels are good. Now, same thing as last time. Now, really what we want to do is we just want to make our mapping notation, right? So let's figure out what our mapping notation is. We have this set up, so we can do it now. So we'll say x comma y gives us, and then our x values will be affected by the horizontal stretch and the horizontal translation. So this will be horizontal stretch of 2, so it's going to be 2x, and then a horizontal translation of negative pi over 2, so that'll be minus pi over 2 for every one of those. And then our y values are going to be at so horizontal stretch of 5, vertical translation of 3, so that's going to be 5y plus 3. And there we go. That's our key for the question. Now we just got to start throwing points into this thing. And then for our reference, it might help to kind of do a little sketch of what we know sine y is equal to sine theta should look like. So that would be starting there, right? And then it would cross through both those points and through there. So we get this tiny little sine wave coming like this, right? And we want to figure out where all those points are going to go. So where is the point 0, 0 going to go? Okay, well actually it will move this time, because this time we actually have some translations happening. So let's see. So we've got the point 0, 0. Where is this one going to go? So this would be 2 times 0 minus pi over 2, comma 5 times 0 plus 3. So this point is going to move to, I should be writing smaller than this, negative pi over 2, comma 3. All right, so negative pi over 2, so that's just going the other direction, right? So pi was 2 blocks, so pi over 2 would just be 1 block to the left, right? So I'm into the left, and then we're going to go up 3. So that point is now there, okay? Next one. So the next one is going to be the point, pi over 2, comma 1. Okay, so doing this one is going to be, so that was our rule up there, so that's going to be 2 times, and then instead of an x, it's pi over 2, right? Which will work out nice. Pi over 2, and then minus pi over 2, comma, and then our y values will be 5 times 1 plus 3. That makes sense. We're going to have 8 for that, right? Which I'm thinking this will be my max point still. All right, so simplifying that down a little bit. So now we've got the 2's cancel there. So we've got pi minus pi over 2. I'll just leave that for one more step here. Comma, and then this is 8, right? So then pi minus pi over 2 is really like 1. This is like 1 pi minus a half pi. So this is like 1 minus a half is equal to a half, right? So this is going to be just pi over 2 still. So pi over 2, comma 8. All right, let's find that point. Pi over 2, comma 8. So pi over 2, that was pi, so pi over 2, and that's going to be all the way up here, this point. And then from here, you've probably got a good idea, even from now, how to just like fill in the rest. Like if you want to go to town just filling in the rest, you probably could. Can you guys see that my next point would probably be right here? Just do the symmetry, right? There's my midline. And then, yeah, I'm going this way. We also could have at the beginning here, I almost should have, right off the bat, our midline, like what we're going around, should be happening at 3. So let's do that now, just even while I'm thinking about it. This, I know, at 3, I should have a dotted line quite often is what we make it, at 3. So this is what the thing's going to be, waving around. And then from here, I bet you guys could even piece it together, couldn't you? Just using symmetry again, right? So if it's like that in the top, this was up 5 over, or like, you know, down 5 over 2. It's going to be the same thing here, right? It's going to be like down 5 over 2. I know I'm going to be right there. And then I'm going to be back up here. And there you go. That's your graph, right? So you can just do it from that if you like as well. You know what? For time's sake, especially this video could be getting a little bit longer, I will do that. But just know I could have also taken this point, and I would have ended up at here. I could have taken this point, or sorry, this point, and I would have ended up at the new minimum. And then that point, and I would have ended up at the new maximum. Or the new, sorry, period, the end of the period there. Okay, let's get rid of those. Okay, all right, so then I'll just connect those dots with the right curves happening here. There. There's our new transform sine function. All right, now we're going to go the other way. So now they give us a graph, and we are going to say what the function is based on this graph, right? So where is this useful, by the way, too? Well, imagine this is nature, and you are actually getting this data, right? Because waves actually show up everywhere in nature, it turns out. As a scientist, we got to figure out what the function actually is, right? What's the equation for this? Now, the way we can piece these things together is through those few formulas. Now, none of them are on your formula sheet, but I'm just going to write them all out again just to kind of remind you. So A was equal to, and it was your max minus your min divided by 2, right? And that's really just going to tell you your amplitude, isn't it? Because your max minus your min would be your whole thing, and then divided by 2 is going to give you just the height from your midline to your peak, right? So that's your A value, formula for your A value. Your formula for your B value, right? It was the absolute value of B is equal to 2 pi over period, or 360 over period. But the other thing we want to do is look at the context of the question to figure out whether or not we're dealing with degrees or radians. And I can see these x values that I've got going on. That's definitely radians. Especially this one ends at 6.28, right? That is the same thing as 2 times pi, right? 3.14 times 2. Okay, so I know I'm dealing with radians, so I'm going to use this one. Okay, so that's my B value. And then my C value is kind of the last one. The C value, what we have to do is just based on whatever function we're basing it on. So in this case, sine. We'll have to like either translate it to the left or to the right, and just go from there. Okay, I'll show you what I mean at the end. So your C, just wait till the end, and then we'll just kind of do what we have to do. But then our D value, you can usually see from the graph, right? So our D value is, well, the graph typically would go up and down around, you know, the line y is equal to 0. And now it's going up and down around this point, right? Which would be the point -1, isn't it? Okay, so it tells us right there. So we can kind of see that from the graph, right? So our D value, yeah, we can tell from there. And your D value, the other one you can use, or the other way to figure that out, is your D would be your max plus your min divided by 2. Okay, so the only difference is like subtracting in that one and adding in this one. So why does this make sense? So your max plus your min divided by 2 is really just finding the average between your max and your min number, right? So if your max is negative 0.5 and your min is negative 1.5, we're just going this number plus this number and then divided by 2 to find the average between those two numbers, because the average between those numbers would be right between those two numbers, right? So that's how we can find our midline. All right, so those are our formulas that we can start with, right? So let's do them one by one. So our amplitude in this case is going to be our max minus our min divided by 2. So A is equal to, okay, our max is negative 0.5 minus, and then our min was, so minus negative 1.5 divided by 2. So A is equal to, all right, so our A value is equal to 1. All right, I'm just going to put a box around that because we're going to use that just to put everything together when we're done here. All right, so we got A. Let's do B now. So our B value is going to require that we figure out our period, right? So let's figure out our period. So we can use whatever we got here. We know that you can find the period from here to here would be the period, but I don't know what that is, right? So that's not going to help me. I do know though that, well, from here to, let's say here would be 1.57, but that's like 3/4 of the way there, isn't it? That's kind of awkward. I could figure that out, but that's a little awkward. I think what'll be easier if I say, okay, from here to here is half of a wave, right? Because, actually, that's not right. Yeah, that is right, sorry. So from here to here would be half of my wave, right? Because that would be my period from there to there, from this minimum to this minimum. So why don't we just subtract 2.62 from 1.57, right? We'll subtract those two and then multiply that by 2 to get the whole period. Okay, so that'll be, so we'll go for your period. All right, you know what? Let's write it over. Let's write it over here. So finding period. So let's go 2.62 minus 1.57. And that is equal to 1.05. All right, so that's how far it is from here to here, right? So we want double that. So we're going to go 1.05 times 2 is 2.1. Okay, so that's my period. So P is equal to 2.1. All right, now why is that useful? Because period and B are really closely tied together, aren't they? Those are the two that, yeah, that are connected there. So B is equal to 2 pi over 2.1. So I can say, like, if you actually just plug all that in, that's approximately equal to 3. It's actually like 2.99199. It's like, it's very close to 3. But it just keeps on going, right? Because I put pi in there, that irrational number. Yeah, so you could call that 3. That'd be a very close approximation. But the other thing we could do here, why don't we make it legit? Why don't I get rid of this decimal by multiplying the top and the bottom here by 10, right? That would work, right? Because if I multiply the bottom by 10, that would be 21. And then I'm making it nice numbers, right? So I'm going to multiply by 10 and multiply by 10. So now that's going to be 20 pi over 21. Okay, that's a perfectly accurate value for B now. Okay, so that's a better answer in the end, right? Okay, so let's put a box around that. So I'll say that's equal to B. All right, we're getting there. We got 2 of the 4 things. So now, actually, we got our D value already, don't we? Our D value, we already said from the graph, you can tell right away that that's equal to -1. It would have worked, though, to put in our max, right? Our max of -0.5 plus -1.5 divided by 2 to get our average, and that would also be -1. So, okay, our D value is equal to -1. Let's do that one. So D is equal to -1. Here, let's just remind ourselves where we got that from for your notes. So D is equal to -1. All right, so now we're pretty good. I think we can actually start throwing this in. So I'm just going to write down the basic equation again. So it's y is equal to a sine b times x minus c, and then plus d. And let's just fill it in. So we know our a value is 1. Okay, 1 times sine, and then our b value was 20 pi over 21. And then our x value, well, sorry, we just say that's x. And our c, I'm going to leave c for a second, okay, because that could change. And then d was -1, right? So -1, we'll say. All right, so we're close. Now let's just think about this because our A value actually and our C value could change based on how we're perceiving this thing. So let's look back at our graph for a second. So this graph, right, started here and then from 0 went down. What do sine graphs typically do? Sine graphs don't do that, do they? Sine graphs go up and then down. Okay, they go up and then down like that. So in that case, well, what we can say here, why don't we do this? Why don't we say this thing flipped upside down? Why don't we put like a negative in front of that 1? Right? Because then that would just flip it across this axis, right? It would flip it across the midline. Because that's what's going to happen when this thing flips, right? They flip and then they translate. So, all right, so that handled that, right? So the -1 part of it. And then what would our C value be? So we're asking ourselves, how did we have to translate this thing to the right or the left to get it to like a sine function, like to where a sine function would start? Well, actually, we don't have to do anything, do we? Because it's already starting from 0. So in this case, our function would just be y is equal to -1, or just negative, sine 20 pi over 21, and then x, and it's just x, yeah. So just x minus 0, or just x, and then -1. So there you go. There is our function. Now I just want to show you that we can change this. Actually, we can make different versions of this thing. I could have also said that this was y is equal to, and then I could have not flipped it. We could have just said that this was just 1 times sine. So 1 times sine. This will always be the same, right? No matter what. 20 pi over 21. And then x. But now our C value is going to have to change because we're thinking about this a little bit different, aren't we? So if this thing didn't actually flip, right? Like I said that this thing flipped upside down the first time. But now I'm saying, since I'm not giving it a negative, this thing didn't flip. What actually happened is that this thing, say I was saying this thing moved or had a phase shift. Let's say this point right here, right? This one we're saying it was here and it moved over there. It moved to the right, right? So how far did it move? Well, it looks like it moved half of a wavelength, or half of a period. Thinking physics here. Half of a period to the right. Okay, so how far is that? Well, that would be the same distance as, here to here, right? 2.62 minus 1.57. I already did this, right? That was 1.05. So this thing moved to the right 1.05. So we can think about it that way as well. So if it's moving to the right, that would be a horizontal translation to the right. And the way we put that in, it'd be minus 1.05, right? Because that's moving to the right. So minus 1.05. Here, I should make that black. And then minus 1, because it's still going to have the same d value there. Okay, so that would also be true. That's actually the same equation, right? If you graph both those things, they'll be identical. Okay. Now, just to make sure that we're on the same track again, we can do the same thing with our cos function, right? It didn't tell us to, right? It said sine in the question, but it could have been cos. And we know that cos graphs actually start at a peak, don't they? So we could have said y is equal to, and then I can flip it or I can not flip it. I'm going to not flip it. So I'll say that this point that was here has moved over, right? So let's say that, because a cos graph would start at the y-axis there and then move over. So let's say it didn't flip. It just moved straight over like that. So this would be cosine, like 1 times cosine, because it's still amplitude is just 1. And then the period would be the same either way, still again. So 20 pi over 21. And then times. And then this would be, well, how far did the cos graph move? Well, it was 1.57, wasn't it? I can just see that from the graph, right? So that would be x, and then move to the right. So this would have been minus 1.57, and then minus 1. Okay, so that would also be true. If you graph this, that would be the same as well. And maybe you kind of see where I'm going here. There's actually like an infinite number of variations that you could do here, because I could say that it was actually that this point moved from here all the way over to there, or all the way over to there, or I could say that it actually moved maybe the other way. So it would be like x plus, however far this is. Okay? So yeah, I hope that makes sense. So yeah, there's actually an infinite number of variations that we could do there just based on whatever it is. So, oh, I missed my square bracket ends there, but you get the idea. All right, so let's keep going here. These ones, lucky enough, these won't take very long. They actually just give it all to you. We probably should have done these ones at the beginning. Okay, so it says write the equation of each cosine function in the form, so they give us in cosine, given its characteristics. So the amplitude 2, period, phase shift, vertical displacement. Okay, so this is just throwing it in. So we'll say y is equal to, here, I'll write it all out, a cos b x minus c plus d. All right, so let's just fill it in. Y is equal to, the amplitude is 2. The period, so here it's a cosine. So I guess they didn't give us everything though. The period is pi, right? So I got a little work to do. I got to find b. Well, b is equal to 2 pi over the period. So that's going to be 2 pi over pi. So then the pi's cancel, right? So our b value is just 2. And then x, and it says we have a phase shift of pi over 3 to the left. So that's opposite, so that's going to be plus pi over 3. And then, what is it, vertical displacement of 1 unit down, so minus 1. There you go. There is our equation. And now we're just going to do it with degrees. So it says an amplitude of a quarter. So y is equal to a quarter cos. And now for the b value, I got a little work to do again. So b is equal to, instead of 2 pi, I'm going to say 360 degrees over the period. And they told me the period was 540 degrees. So 360 divided by 540, which simplifies to 2 over 3. Okay, so my b value is 2 over 3, so I'll just throw that in, 2 over 3. Remembering that what's actually happening there for the stretch would be 3 over 2, right? You'd flip those upside down, but this is literally the b value that I'm finding, so I'm just going to put it in as is, just 2 over 3. And then times x, and it has a phase shift of 60 degrees to the right, so that would be x minus 60 degrees. And then a vertical displacement of 2 units up, so plus 2. There you go.